Ever wondered why an AI that seems super smart in the lab can stumble when faced with real-world data? Imagine a hospital using an AI to predict patient outcomes. It's trained on data from one hospital, but when deployed elsewhere, the records are structured differently. Suddenly, the AI starts making weird mistakes. This is the problem of missing data shifts, a critical hurdle in making AI reliable. So why is missing data such a big deal? Think of it like solving a puzzle where some pieces are missing, and the pattern of missing pieces changes every time. Traditional methods try to fill in gaps with averages or guesses, but if the way data is missing shifts, those fixes fall apart. For example, one hospital might record blood pressure every hour, while another only does it when it's abnormal. An AI trained on the first might completely misfire on the second. That's where MIRRAMS comes in, short for mutual information robustness for missing data. It's like teaching a model to focus on the big picture, instead of getting stuck on missing pieces. How? By using mutual information, a fancy way of measuring how much one piece of data tells you about another. Imagine an AI recognizing a cat whether the image is blurry, flipped, or partially hidden. MIRRAMS does something similar, but for missing data. Here's the magic. MIRRAMS trains models to extract label-relevant information while ignoring how data is missing. It does this by simulating different missingness patterns during training, like practicing with puzzles where pieces are missing in all sorts of ways. Then it uses a special loss function, a mathematical recipe, that rewards consistency. If the model's predictions stay stable even when data is masked differently, it's learning the right patterns. What makes MIRRAMS stand out? It's not just about handling missing data, it's about understanding why other methods work. One of its loss terms closely resembles fixed match, a technique used in semi-supervised learning. This bridges gaps between different AI approaches, making MIRRAMS a versatile tool. The results? MIRRAMS outperforms traditional methods across diverse datasets, even when no data is missing. It's like a Swiss Army knife for machine learning, effective in both supervised and semi-supervised settings. And because it's built on foundational principles, it can adapt to images, text, and more. So next time you hear about AI failing in the real world, remember, challenges like missing data shifts are being tackled by clever solutions like MIRRAMS. By building models that thrive in uncertainty, we're making AI more reliable, and that's a game changer for healthcare, finance, and beyond. But how do we actually measure if a model is good? Let's dive into a study that tested machine learning models on real-world datasets. Researchers looked at datasets like adult, predicting income, arcene cancer detection, and arrhythmia heart data. But here's the catch. Some of these datasets are tiny, like solving a puzzle with half the pieces. To prevent models from just memorizing the data, they tweaked the models themselves. For example, they simplified the arrhythmia model's design and adjusted the layers in arcene, like customizing a car's engine to fit the road it's driving on. How do you measure if a model is good? Enter AUC scores, a metric that tells you how well a model can distinguish between two things, like spotting a cat versus a dog. Higher AUC means better performance. The study tracked these scores across multiple tests, plus their standard deviations, which show how consistent the results are. Think of it like a sports team's performance. A low standard deviation means they're reliable, while a high one means they're all over the map. Take the adult dataset, for instance. Models like XGB and SAINT scored over 90% AUC, but the team's own method, ours, outperformed most, especially when the data was noisy or scarce. Imagine a runner who's not just fast on a track, but also adapts when the path gets muddy. On arcene, where data is super limited, ours stayed steady while others faltered. This matters because real-world data isn't always perfect. Sometimes you're working with just a few hundred samples, not millions. Here's the twist. No single model is a superhero. But the study shows that tweaking parameters, like simplifying a model's structure or balancing complexity, can make a huge difference. And when you pair that with smart algorithms, you get models that are both powerful and reliable. So next time you hear about AI doing something amazing, remember, it's not just about fancy tech. It's about understanding the data, fine-tuning the tools, and making sure the results hold up. Thanks for watching. If you want to dive deeper into the datasets or the math, check the links below. Stay curious.